It's not working. There we go. Hi, everyone. Once again, thank you so much for joining us today. This is the third and final in our Heterogeneous Compute series. And the title today is Enabling Heterogeneous Compute with Gen Z Fabric Management, and will be presented by Jim Hall from IntelliProp and Russ Harrell from HPE, both member companies of the Gen Z Consortium, and will be followed at the end with a Q&A session. So if you do have questions, please feel free to comment those in the chat throughout the presentation, and we'll take note of those and respond during the Q&A at the end of the session. So for now, Jim, Russ, if you'd like to take it away.
Rachel, this is Tracy. I told those guys I'd do the early introductory slides and then they'll take over the technical part. So my name's Tracy Spittler. I'm with IntelliProp. I'm also the co-chair for the Gen Z Consortium Marketing Working Group. So with that, we'll get started. So let's move to the first slide. So just a quick overview of what we're going to be talking about. I'll just present some high-level hardware, software, Gen Z system overviews to get us all hopefully on a level playing field. And then Russ will talk about the work being done in Open Fabric Alliance. And then Jim will take over the remainder of the presentation, and hopefully we'll have time for a live demo of what work has been done with the Gen Z Fabric Management software work. So let's go ahead and pull up the high-level overview of Gen Z system. So we have, and some folks have probably seen this before, but on the left side, we have an example hardware Gen Z topology. There's a kind of a main host and other host node servers. And then we have a handful of Gen Z memory controllers at the bottom of the screen, all communicated through a Gen Z switch. So that's a example hardware topology. Gen Z has a lot of flexibility such that you could add more or less of any of these components. On the right side is an overview of what the software stack looks like. Again, Russ will be talking about the Open Fabric Management Framework, which is the top part of the Fabric Manager GUI, the Composability Manager, and the Resource Manager. And then Jim will be getting into the lower level Gen Z specific software components. We'll talk about what Zephyr is, what Llamas is, and what a little bit on the Gen Z Linux driver. So let's go ahead to my last slide, which is just an overview of kind of the breakdown of that software. And I did just kind of give a description of that. So it is done, the top part of the software stack is being done through the Open Fabric Alliance. And we talked about the components there. The Gen Z specific stuff, we have a Zephyr, which is a fabric manager that runs on a single node, typically within a Gen Z hardware system. And then we have what's called Llamas, which manages the local components attached to each server node. And then at the lowest level, we have a OS Gen Z driver, which is specific to whatever Gen Z bridge is communicating to the Gen Z fabric. With that, let's move to Russ's OFA overview slide. Russ, take it away.
Assuming everybody can hear me, the image on the right is sort of a bubble diagram representation of the software stack for an example management system. And I'm just going to walk through the steps that are involved in making some changes to the fabric as a way to illustrate the various roles that are depicted over here on the right. So next slide, please. So applications, you want to launch an application on your fabric. And so the application requires resources. And typically in these kinds of scenarios, it's quite common that the application references a template for a platform that it wants to run on. So next slide. The admin or orchestration tool parses the workload templates and sorts out what the application wants. And the admin requests some kind of composition tool create this logical platform. And the composition manager will then request logical resources from pool managers to create the desired logical platform. So all of this stuff occurs in tools that are above the OF management framework. But when those tools are ready, next bullet, they keep track of their logical platform resources, and next bullet, and they make requests for logical changes to the fabric through the OF-MF layer. The pool managers, they evaluate inventory and they craft logical resources from the physical resources, and then they return OF-MF redfish URIs for the requested objects. Next bullet. And they will track their logical and physical resources that they are managing. And then they will also request physical changes to the fabric to instantiate any logical resources that they are needing to make present on the fabric. So these upper layer managers are clients of the OF-MF redfish model. Next bullet. So the OF-MF gets these requests from the clients. Next bullet. And it updates the redfish model for the fabric that it is maintaining. And that is where the magic of the OF-MF occurs. It matches a redfish model of the fabric with the requests from the clients to manipulate the fabric resources. And then it requests that the provider modify the fabric hardware to match the intended setup and supply some runtime fabric services after the applications are up and running. And so the OF-MF coordinates all of these upper level activities for managing the fabric with the fabric provider, which has a proprietary model for its fabric resources that it is physically in control of, and gets the fabric manager proper, if you will, to actually make the changes to the hardware. Next bullet. So these fabric specific manager routines do the actual management of the hardware, and the initial configuration is fabric specific. But once the fabric is initialized, the OF-MF presents a coherent redfish model to all the upper level tools, and the upper level tools do not need to know the details about the specific fabric or fabric manager. They just manipulate redfish objects to get the fabric configured the way they need it. And so that's the whole principle and theory of operation of the OF-MF services layer, which is what the OFA Open Fabrics Management Framework work group is striving to produce. And Jim is going to take you through all of the things below the OF-MF and provider layer in terms of what goes on in the Gen Z fabric management stack that is the lower half of all of this. So Jim?
Actually, if you just go back up one slide real quick, this is Tracy again. So I don't know if anyone else has questions, because it's kind of a break point between what is being done in OFA and what is being done specific to Gen Z. I'd like to see if anyone has questions, and Russ, I'll ask a question. All this is part of the Open Fabric Alliance work, and that's true that this is all open for participation by any individual or member or companies? Is that true?
That is true. The OFA has completely open membership. So the work that we're doing in the OFMF services layers is open to participation from anybody. You do not have to even be a member of an employee of a member company. Private individuals can join in here at the OFA.
And one other question, all this work that's being done is available via a repository, public repository?
Yes, there are public repositories for the OFMF work that we're doing. And I believe that we have public repositories for some of the fabric provider work that's going to be done as well. And then, of course, the Linux Gen Z subsystem is also public, but Jim will tell you about that.
Okay, great. If no other questions, then let's jump in with Jim.
Okay, can people hear me?
Yes.
So we're now going to focus on the lowest bubble from Russ's slide, which is what's going on in the Gen Z fabric management space. This slide will build starting with this picture of what an example Gen Z fabric topology might look like. In this example, we have 3 hosts, each with a Gen Z bridge connecting that host into the Gen Z fabric, specifically to a Gen Z switch. And at the bottom, we have a set of other fabric visible resources, including Gen Z memory modules. Those are the ZMMs, and maybe an accelerator if there is one of those. Next bullet, please. So what happens in the OSs is that a Linux OS, as an example, discovers this local bridge hardware and binds a bridge driver to it, and it uses existing native buswalk methods. So if that bridge hardware appears as a Gen Z device as PCI, or in ACPI, or even in an embedded system using device tree, those are the methods that are used to find that Gen Z hardware. One of these nodes is designated as the fabric manager, and it runs a fabric manager process called Zephyr that runs in user space, not in the kernel, which is different than the way PCI discovery works. As an example, here we've moved it into user space because it is fairly involved and there's lots of policy decisions that you wouldn't want to embed in the kernel. And that fabric manager has a northbound interface which uses JSON to talk to the higher levels of Russ's OFMF stack. Now, every node in this fabric, every host node, also runs something called Llamas, the local Linux local management services. And that exists to talk to Zephyr on the one hand, and to the local kernel Gen Z subsystem on the other hand. Llamas contacts the Zephyr Fabric Manager over whatever networking technology might exist. In this example, it's over Ethernet, but it doesn't have to be Ethernet. And then it sits around and waits for Zephyr to tell it what to do. Next bullet. The Fabric Manager, when it starts up, is going to use the bridge hardware and the kernel subsystem services to do a recursive walk of the Gen Z fabric and discover all the components that are out there. And it sets identification information, including something called a GSID, a global component ID, in each of those components. It sets up routing tables and does all the fabric initialization that's necessary to allow communication to happen. Next bullet. Now for each of the nodes running Llamas, Llamas is going to receive an add component command from the fabric manager telling it that there's some new resource that this particular host is supposed to see on the fabric. And that Llamas instance will send its local kernel a corresponding Netlink add component command. Now Netlink is an existing Linux standard feature that allows user space to make calls into the kernel using a kind of socket style, as opposed to various other mechanisms that user processes have to talk to the kernel. Next bullet. Now for those discovered components on the fabric manager node, Zephyr is sending Netlink add fabric component command. That's a different command. And it's different because we want the fabric manager to be able to see all the resources on the fabric, but not necessarily bind drivers to them, because it may not be the host that's supposed to see those particular resources. It may be one of the other ones. Next bullet. This model also supports the idea of Llamas receiving remove component commands from the fabric manager and therefore tearing down the local OS view of fabric nodes, but we have not actually implemented the remove yet. Next. Okay, so I mentioned Netlink before as the communication method from user space to the kernel. This is just a little more detail about the two different styles of Netlink commands. The first one is actually labeled wrong on this slide. It's the add fabric component command, not the add component command, and it instantiates those resources in the /sys file system, again, a standard part of Linux, under /bus gen z. And each fabric gets a number, each subnet on the fabric, which is another Gen Z concept for allowing huge fabrics, and each component gets a field in the /sys file system under sysbus Gen Z fabrics. And on the other side, the Llamas controlled resources, they appear under sys devices, and that's the important distinction between what's happening with the fabric manager and the Llamas resources. Sys devices is the place in Linux where if something appears there, then it is likely that the system is going to attempt to bind a local driver to that. And then we have the remove component, like I mentioned. Next slide. Diving down one level in the stack now and talking about what's happening in the kernel space. We have three main kinds of drivers in the Linux subsystem environment. First is the bridge driver that we've talked about before, discovered by the native discovery method. It will register with the Gen Z subsystem, which is another module in the Linux kernel. And that's how the Gen Z subsystem knows that there is a bridge driver and that there should be a fabric out there. And it implements a set of APIs to allow the subsystem to read, write, and mmap both control and data space regions of the discovered Gen Z components. Then there are Gen Z device drivers, much like you would bind a PCI device driver to a specific PCI device. You can have one that binds to a Gen Z component, for example, an accelerator like was shown on the one of the earlier slides. And it works much like PCI does, except that instead of using vendor and device IDs, which are registered and maintained by the PCI consortium, Gen Z does binding by something called a UUID, a unique, universally unique identifier, which means you don't have to have a central authority that's managing those IDs. And as I mentioned before, different than PCI, we use probing that is controlled by Zephyr messages to Llamas and Llamas Netlink messages into the kernel rather than doing all of that discovery in the kernel. And then there are a set of sort of special generic Gen Z resource drivers. And again, these drivers are bound to a resource region of a component, not to the full component itself. And so this allows us to take a Gen Z memory module as an example and split it up into multiple regions, and not hand the entire component to a particular host, but just a region of that component. And those drivers exist in several forms. The first Gen Z block makes those resource regions of Gen Z data space visible to a host or more than one host as a DAX-enabled block device. DAX here means device direct access extensions. Again, a standard Linux thing which allows you to not do block transfers to that block device, but instead mmap that region all the way up into user space and allow it to do direct load store to the file or block device. A second special driver is called DAX Gen Z. It allows you to take Gen Z resources and make them visible as a device DAX device with a special character device named /dev/dex n.m. Again, this DAX infrastructure is standard pre-existing Linux infrastructure. It was originally invented by Intel for persistent memory, but we're by adding this new DAX Gen Z device, we allow Gen Z resources to also appear as DAX devices, and that allows the any existing code that might be written using Intel's persistent memory device kit or PMDK to use Gen Z devices now. Two future additions are Gen Z Mem, which would allow taking that region of Gen Z data space and making it appear directly as system memory on a host. We'll see, in fact, that that's not necessary to do system memory. There's a way to do it via DAX, and we'll see that hopefully in the live demo. And then Gen Z ENIC, which creates an emulated Ethernet network among the Gen Z nodes on the fabric, so that you don't have to have wired up a parallel Ethernet fabric. You can use Gen Z itself to route Ethernet traffic. Next. All right, before we get to the actual live demo, one last slide to talk about the environment that I'm going to show. We have an even simpler system topology than was represented earlier on those slides. This is some hardware called the Gen Z Micro Development Kit, or UDK. It consists of a Bitware 250 SoC FPGA, which has an Orthos host bridge bitstream programmed onto it. That card has embedded ARM processors that are running Linux. So instead of this card being plugged into a host and the Linux running on that host, this card is the host in some sense. And it has an integrated Gen Z host bridge. And then we have two Gen Z memory modules. Unlike the example topology earlier, there's no discrete switch. Instead, we're taking advantage of a Gen Z capability, which allows basically any node in the fabric that has more than one interface to not only be, say, a memory module, but also to route traffic from one interface to another as a integrated Gen Z switch. And so in this topology, you can see that in order to get to the bottom ZMM, we have to go through the top ZMM to get to that bottom one from the Orthos card. So let's now try to configure a fabric, add a Gen Z block device, and add a ZMM memory range to that host. So I'm going to take over sharing the screen so I can do the live demo. And if someone could tell me whether they can see what I'm sharing.
Yes, I can.
Okay, so in the background here is the same slide we were just looking at. I'm going to keep that here so that you can remember what it is we're doing here. There's two main shell windows here. This bottom one is the one that I'm going to use most. It has a set of tabs along the bottom, which are just different SSH instances into the 250 SoC Orthos card. On the top is another window that lets us see the serial console of the 250 SoC, as well as serial consoles for debug of the ZMMs. Hopefully we won't be using that very much because things won't go wrong. So let's start here in the bottom window by running lsmod. That's a standard Linux command that tells us what modules exist. Right now there are basically none, and there are no Gen Z modules loaded. Normally you would have those discovered and loaded automatically, but I've configured this machine to not do that so that we can see the steps more directly. And a command we haven't talked about yet, but one that exists, just like PCI has an ls PCI, we have an ls Gen Z, which shows you what Gen Z components there are. And right now there aren't any because we haven't loaded the modules. So I'm going to run this script, which is very simple. Basically, it's just loading the modules. And you can see in the top level that a bunch of debug stuff came out in the bottom window as well. And if we run lsmod, you can see now there is a Gen Z subsystem module, and there is an Orthos driver that is connected to the Gen Z subsystem. And if we run ls Gen Z again, you can see that now we have found that there is a bridge. That's the local bridge. These long strings are UUIDs and serial numbers. And this last thing here in the end C config says that this module is in the ready to configure state in Gen Z. It is not up and ready to be used. And that's because we haven't run Zephyr yet. So let's do that. I'm going to run it with some verbose options so that we can see what's going on. And it has done a bunch of stuff. If you were to look at all that log info, you would see that what we're doing is exploring this fabric. We're finding the various components. And we are now running a Flask client, which means that we're ready to accept network connections from higher levels of the management stack, including connections to Llamas. But before we run Llamas, let's see what's happened to ls Gen Z. And you can see now that we have found 3 components, not just the local bridge, but 2 memory modules as well. And they're not in cconfig anymore. Now they're up. And if we run this with slightly more verbosity, we also get detail that shows that our bridge has one interface that's down and one that's up, because the first one is down because it's not connected to anything. The second one goes to that component number 2. Component number 2 is the memory. It has 4 interfaces, 3 of them are up, 1 connected to Orthos and 2 connected to the ZMM. And the last ZMM has 2 connections as well back to that first ZMM. Those of you who are paying close attention to the diagram in the back here might think, well, why are there 2 connections between the ZMM? I only see 1. And it's true, there's only 1 cable connecting them, but it turns out that the backplane that these ZMMs are plugged into has a kind of hidden, always there Gen Z link. So in this case, there are 2 links between those 2 ZMMs. What we can do now that we have Zephyr running and we've found our components is we can run Llamas. And it's going to contact Zephyr, and it's going to get told what resources it's supposed to see. Now, you might wonder, well, how does it know what resources are supposed to be seen by this host? And the answer is that there's a static configuration file that Zephyr maintains that tells it what components should be made visible. And if we run these commands, ls block, ll devgen of dev dacstar, and ls mem, we can see here that there is now a Gen Z block device of size 36 gigabytes, because that's what the config file told it to do. And we can see that there at this point is one DAX device named 0.0. You have to trust me that that's a Gen Z DAX device. There's no other way to know from the name here. And you can see that at this time, the kernel thinks it has 4 gigabytes of memory, and none of it's Gen Z memory because we haven't told it about any Gen Z memory yet. This is just the standard DRAM that's in this 250 SoC. But what we can do now is come up to this window. One of the times I'm going to use this one. I'm using it because I need to be root to do these commands, and it's just a little easier. The DAX infrastructure, again, a standard part of Linux, lets you take these DAX devices and unbind them from the device DAX driver. So we're going to do that. And then we can rebind them to something called the DAX KMEM driver. And what the KMEM driver does is it lets you take a DAX device and turn it into standard system memory or kernel memory. And so now if we do that and we repeat these commands, you can see we still have a block device and we still have our DAX device, but instead of there being 4 gigabytes of memory, there's now an additional 31 gigabytes of memory that is being supplied by that Gen Z device. Now you may notice that that memory is offline. That's because this kernel is configured not to bring new memory online automatically. And in fact, I'm not going to do so because if I did, you would run into a pre-existing hardware bug in the Orthos system where as soon as you do that, it will hang. So we're not going to do that. But we are going to do one other thing, which is, bring one more window in that I didn't tell you about. So I mentioned that Zephyr currently has a static config file which determines what resources should be made visible. But it also has the northbound interface that lets new commands come in. And so if we run this little script, which basically has a curl command in it, and we run it against this particular configuration file that represents another DAX device, this one 22 gigabytes in size instead of 32 gigabytes in size. And we tell it we want to run that against the 250 SoC1 or the Fabric Manager. We can see that we get some log messages about what resource was just added to Zephyr, and we can see that nothing failed and that there is success talking to the Llamas instance at this particular URL. And when we run these commands again, now you can see there's 2 DAX devices. We added a new DAX device 1.1 to the Fabric at runtime. And if we wanted to, we could at this time add DAX device 1.1. We can unbind it from the DAX driver, and we can instead turn it into kernel memory. And when we run this command this time, now we can see that there's 52 gigabytes of potential offline memory, including an extra 21. Now you might wonder, well, it was a 22 gigabyte device that I added. Why am I only getting 21 gigabytes of memory? And the answer is that part of that memory is being carved out by the kernel to hold struct page structures, which are necessary for every page of physical memory in the machine. And so you can't get all of that memory. And in fact, there's a granularity issue here, which is that you can only add memory to this kind of machine, which is an ARM-based machine in 1 gig increments. And so we only get 31 out of 32 and 21 out of 22 gigabytes. The other thing we can do is do something with this block device that I added here. So I have a script which is called setup, and its job is just to make this demo a little easier. What it's going to do, well, that's not good, is set up file systems and partitioning. And so if we run ls block now, we can see that this Gen Z device has now been carved into 3 partitions, again, standard Linux stuff. And we've put a file system on partition number 3. And we could now run commands against files there if we wanted to, because it's a standard block device with standard file system. And I think that's about it for my demo. I'm going to stop sharing and we can go back to slides.
So I'll kind of wrap up the slides. Thanks, Russ, for the higher level description, and thanks, Jim, for lower level description and that demonstration. So to recap and kind of talk about what is currently going on, Russ talked a bit about OFA development and the availability for anyone to join that, but their current, he walked through the top level stack, but currently they're doing emulator development, which will allow folks to take the OFMF structures and run it against Gen Z lower levels. And they're also working on, as I think he mentioned, some of these redfish extensions. And then from a lower level, the things that Jim talked about, the Gen Z specific fabric development. Currently, there is a limitation where Zephyr has to be available when Llamas is started. That will change in the future where Llamas will initialize prior to Zephyr being visible. Some of the things that allows will allow us to eventually do in-band configuration. Jim mentioned that currently Zephyr will talk to Llamas in the sample or example via Ethernet, but eventually Zephyr will be able to talk to Llamas via in-band Gen Z. So there would not necessarily be a requirement to have a separate network attachment between hosts. And then obviously we want to connect the top level and bottom level together through integration with the OFMF framework. And then something big on the horizon in November is pulling this all together and showing it at Supercompute 2021 in St. Louis. Rachel, if we can go on. So there are opportunities. I think Russ mentioned open membership into OFA. Certainly, I think they welcome folks to contribute, test, write code. A quick search for Open Fabric Alliance, I think will get you to their website. The lower level stuff, there's also opportunities to collaborate on the development effort. Some of the stuff Jim showed, we certainly welcome folks to participate via coding, collaboration, feature planning, testing, integration work. And those contacts can be made through the Gen Z Consortium website, and the folks there will get you to the right people. That collaboration is currently a multi-company collaboration. All right. I think that's it for the presentation. Rachel, do you want to lead Q&A if there is any?
Absolutely. So if anyone does have any questions, please, as I mentioned, feel free to use the chat feature on the right side of your screen. Or if you'd like, you can unmute and ask your question directly. But please go ahead with any questions that the group has. Okay. Well, as we mentioned, we have recorded this call. You will be able to find this on the Gen Z website, genzconsortium.org. And please do follow us on Twitter and LinkedIn for updates and additional information. We will be starting our new fall series of webinars coming up in August. So please stay tuned for that. And oh, we do have one question that has come in. We have just a moment. So from Alistair, the bug in Orthis that meant the memory couldn't come online, is this to be fixed?
Absolutely. We know what's wrong. We just don't have a fix yet.
So I guess a little more clarification on Orthis. That is a kind of at a prototype stage, and there are features and bug fixes ongoing. The fact that it's in FPGA hardware means it's certainly flexible to absorb future feature changes and bug fixes as we go.
Great. So as I was mentioning, we are going to start a new series in the fall, beginning in August. Be on the lookout for that. We are going to be having more coffee chat sessions as well between now and that time. So we do hope you'll join those. You can stay up to date by visiting the website, checking out our event section, and also following us on Twitter and LinkedIn. If you do have any questions after this call, please feel free to contact us through the website. We'll pass those questions along to the appropriate person. And with that, thank you so much to Jim and Russ and Tracy for today's presentation. And hope everyone has a wonderful remainder of their week.
Thank you, Rachel. You too.